to lecture 88. So, we have been discussing one problem on interplanetary transfer, and there we were looking into the Hohmann transfer, and we found that the astronomer on asteroid A has to wait for 390.8253 days. Now, we have to calculate also the time that it will take to go from. So, time of travel from asteroid A to B. So, how much time the spaceship will take? So, this is simply the half time. Okay. T we have written as this as T, which is pi times the mean radius 2.7, the semi major axis 2.75 r whole cube divided by mu. And if we insert the value for the r and the mu here in this place, we get this as 719.56309 seconds, and this equal to 832.82765 days. So, from going from asteroid 1 A to asteroid B, it takes 832.82765 days. Once we have done this, then he also plans the return journey. Okay. So, it is important to know what are the angles of these two asteroids with respect to each other. And that we can compute as follows: angle covered from epoch by asteroid A during waiting time and plus transfer time. So, this we can write as theta prime A. This will be theta A plus delta theta A. This is related to your wait time and plus transfer time. Okay. So, this is pi times 2.75 r whole cube divided by mu. This is the time. So, multiplied by omega A. So, omega is known to us, all other quantities are known to us. Delta theta A already we have determined, delta theta A already we have T A we have determined. So, delta theta A, this is the quantity omega A times wait time. So, T W and on A, T W A. So, omega A is known to us, and T W A we have already calculated. So, we can write this part here 7.0393902 into 10 to the power minus 8 radian per second, and multiplied by the wait time, which is 33767308 seconds. Okay. So, this turns out to be 2.3770126 radians. So, 2.3770126 radians. this is delta theta A. Theta A is known to us. So, all these quantities can be added. Now, this quantity also needs to be evaluated. So, the quantity here pi times under root 2.75 r whole cube divided by mu times omega A. This is already known to us. This is the transfer time, this quantity. So, this is your t transfer time, or which we have written as t equal to t 1 by 2 as written here. So, this is the transfer time. So, this is your 71956,309. These days we are not using, remember, we are using seconds, because omega A is in radian per second, and this multiplied by omega A, which is 7.0393902 into 10 to the power minus 8. So, this gives 5.065284 radians. Now, if we add all of them, so theta A, it is already given to us 139 degree plus delta theta A, which we have written here 2.3770,126, and this quantity, this also we have got, this is in terms of radians, this is total angle. Okay. So, during the flight time how much A moves. Okay. So, this we add here 5.065284 and times 180 divided by pi. So, this gets converted into degree. Therefore, we get from this place 565.4122 degree. So, what we have got here, theta A prime, this equal to 565.41227 degree. So, this is measured from the epoch. So, that means initially theta A was given to be 139 degree. So, your A was here, okay, and this was your theta A, and thereafter it moves. So, finally, the theta A prime. So, there is a wait time. During the wait time it moves certain distance, and then during the flight time it moves certain distance angle, and that total angle turns out to be 565.41227 degree, and if we subtract from this 360, say 41227 5, this is 0, 205 degree. So, that means from measured from this place it crosses it and then again comes to 205 degree, means somewhere it may be, say here 180 plus 20, 205 degree more. So, somewhere it may be in this place. So, this point we show this as A triple prime, and this I will remove because this is not required now. Theta A is not required. What we are concerned about? The new position. So, this is the new position. This is theta A prime. Now, the same way we also need to know where the asteroid B is located, because again he has to start from asteroid B and go to asteroid A to get his Geiger counter. So, from epoch the position of this particular example, this will clear you what is happening, and thereafter we can do mathematics. From epoch the position of asteroid B at the time when spaceship reaches B reaches asteroid B can be written as theta B prime, and theta B prime will be how much? Theta B plus wait time, which is W B times T W. Okay, wait time is same for both A and B, or either you can write here T times W A, and then during the flight time how much the B will move, or simply we can write here theta B plus delta theta B. So, delta theta B perhaps we have not evaluated here, delta theta B we have not evaluated, or either simply you can write theta B plus delta theta B. So, the quantity which we are writing here, it will be delta theta B, omega B times pi under root 2.75. This is the time in the time spent in the, or the time of flight of the vehicle from A to B. Okay. So, 2.75 r cube divided by mu. Inserting all the values, now omega B times T W A we have to first determine 0.4 29 radian. This whole thing is delta theta B, and omega B times pi 2.75 r whole cube divided by mu. This quantity similarly it can be determined, we just have to insert those values. Okay. So, this turns out to be 3.0407308 into 10 to the power minus 8 times 956309. And adding both of them you get here delta theta B. So, theta B prime then gets to the value, this is 271 plus 1.0267729 plus 2.1879977 times 180 divided by pi. This is the quantity your delta theta B, and this equal to 455.19278 degree. So, what we have got, theta A prime is equal to 565.41227 degree, and theta B prime, these are all measured from the epoch. measure from the reference line. Okay. On that particular epoch is a particular date and we are measuring it from the reference line, which we have shown earlier. This is your reference line. I have shown this as the gamma 0, which may be treated as the vernal equinox. So, these are the angles and difference between them delta theta b or simply delta theta we can write as 110.21949 degree. So, this is the difference. Now, we can solve the part B. This is important for solving part B. So, return journey. In the return journey, let us say this is the position of B. This is the position of B, and with respect to this, A is ahead by 110.219 degree. So, 90 and then 110, 90 and 20 degree more. So, A is somewhere located here. A is located here in this place. And this is known to us, which is delta theta we have written equal to 110.21949 degree. So, it is asking, the question was that when he arrives at B, he finds that he has missed his Geiger counter on A, decide to go back, then what is the minimum waiting time on B if he return journey is made under fuel economy condition. So, again the wait time on B has to be, earlier it was wait time on A, now he has to wait on B, because the spaceship is on this. So, right now this is the situation, this angle is given here. So, let us say that the astronomer has to wait on this, and by this time it is going to B prime here. So, this is the wait time in terms of written in terms of angle. So, this is again T w. This is another problem, T w in this case this will be different, or either we can write in terms of T w prime, or if we write here wait time on B as T w B here. This is the waiting time on V while the astronomer is on the B. So, in that time it will cover angle. So, the angle from this place to this place is this much before the launch can be done, okay. And then the launch is done. So, if the launch is done from this place, and B double prime will come here in this place. So, during so launch is done from B and it has to go on A. Therefore, this comes here and the Hohmann transfer is. So, this is A double prime I will write. Why? Because first during this wait time from here to here, your A is already here. So, it will move certain angle, okay. And because this is fast moving, A is fast moving, this is in the inner circle. So, it may come to some other point, let us say it comes here, okay, or either it comes here, whatever the position. Okay. So, in this wait time, let us assume that this comes to this place, this is A prime, and from A prime then during this flight time, This is your flight time, which we are writing as t. And whatever we have calculated earlier, the flight time, the same thing is applicable here in this place, because the semi major axis does not change, and therefore, flight time also does not change. T equal to the semi major axis remains same, a q by mu under root times 2 pi. Here a is 2.75 r. So, a prime is here. So, a prime we get what, that this a moves to a prime during this wait time, and thereafter during this flight time, then a will move from this place and it will come to, all the way it will move from here and then it will come to this place. So, during that time the ship which was launched here, while the A was located at A prime. So, the ship is being launched from B prime. Okay. So, it arrives here. So, in the same time the asteroid A also arrives here, and thereby the spaceship will land on A double prime, and here we are neglecting the gravitational field of both the asteroids. If we do not neglect, then we have to take into account the patched conic section, which we will do later on. We first finish this part. So, therefore, we can write from this place delta theta plus delta theta is what? This angle. This is delta theta plus delta theta A, which is the wait time. Wait time is from this place going up to this place till A prime. Okay. Angle we can show it like this, going from this point to this point. This is delta theta A, and then flight time, which is omega A times T w, which is pi times simply T, not T w. This is time period is 2 pi. So, half only we are considering. So, there we have to multiply just by pi. So, pi times A cube, which is 2.75 r whole cube divided by mu. This is the total angle covered, and this must be equal to delta theta b, which is your here delta theta b. This is the wait time, and then the launch time from moving time from this place to this place, which is 180 degree. So, delta theta is given to us, this is 110.21949 degree. Delta theta A, this is not known to us, and flight time, this is known to us. This flight time times omega A, okay. This quantity is known to us. Okay, little bit there is a twist which we have to take into account while working with this. So, already we have looked into that the A will start from this place, it will move by delta theta A here, and then again from this place it will come to this place. So, we have to properly account for this fact. Okay. On the right hand side, so in the meanwhile, B starts from here, B is here, and during the bed time it has moved through this delta theta b, okay. And then the flight starts from this place and it goes to 180 degree, and then the earth is getting covered. So, this is delta theta 180 degree plus delta theta b equal to this angle, but there is some twist. You can see that b is located here. So, it is a coming here only in this place, a is located here. Okay. So, it goes all the way to this place and then it comes here in this place. First it goes here, from A to this place, this journey is there, it may be, okay. And then from A prime, then the journey starts and goes at, ends up at A double prime. So, in this way A has covered more than 360 degree, if you look here in this place. Okay, and this particular thing we need to account for. So, here this quantity then what we need to do, that say we subtract here 360 degree from this place. So, this locates the, this is the total location delta theta was your angle, this one, okay, as shown here, this is your delta theta, this angle. So, delta theta plus delta theta a, this is coming to this place and then again going back, and we are measuring, and this we have the position of B we are taking as a reference line. So, one way we could have also written this whole quantity as delta theta a rather than writing here in this way. So, let us say this is delta theta a prime, we write here in this way, which is the total delta theta a plus omega a plus the flight time, whatever it is, and then we need to solve it. Okay. So, delta theta a prime, this includes the time in which move from B prime, the delta theta a prime also includes move from B prime to, in which the spaceship, rather we should write in which the spaceship will move from B prime to A double prime. This also includes. So, therefore, we have delta theta B plus 180 degree, this equal to delta theta is already given, this quantity 110.21949 degree, and plus delta theta a prime we are writing here, and minus 360 degree. So, delta theta a prime, this equal to delta theta b plus 180 degree plus 360 degree minus 110.2149 degree, 2194949 degree. So, this quantity turns out to be 429.78051 degree plus delta theta b. and if we convert in terms of the radians, so this will be 70851 times pi by 180 plus delta theta b. This is in radians. Delta theta a prime, which is the quantity summed up, delta theta a plus omega plus the time of travel. So, we can delta theta a prime divided by omega a is equal to delta theta b by, now equating time. First we have balanced angle, so equating time or balancing time. So, delta theta a prime divided by omega a, this is the time, wait time, and plus the travel time, plus the travel time. So, during that period b will move by delta theta b by omega b plus t, the half period, t equal to t 1 by 2. Okay. Going back here, so delta theta b and this divided by omega b. So, this is the time taken to from this place to this place, and then the travel time, which is t. This should be equal to the total angle travelled by a. Okay. The angle travelled by a, which we can write here like this. Here you can check that we have multiplied by omega a. So, this is the angle travelled by a in the flight time. Okay. So, this is t, then we can insert these values. T is already known to us from the previous calculation. So, this quantity is your 71956,309, this does not change. And then we solve this. So, we can utilize the previous information, delta theta a prime equal to this quantity. So, this is equation 1, let us say, and this we have got as equation 2. So, inserting delta theta a prime, inserting 1 into 2. So, if we insert, so this becomes 7.501085 plus delta theta b by omega a seven 71956,309. And solving this, so on delta theta b divided by omega b, if we take it outside, one minus omega b divided by omega a, this becomes, and this equal to on the right hand side 7.501085 divided by omega a minus 71956,309. Now, 1 minus omega b by omega a is equal to 1 minus 3.50 407,308 divided by 7.0393902. This quantity, okay, and therefore, from here we get delta theta b by omega b. This quantity will turn out to be this quantity omega v we have to insert here in this place. So, this whole value, this will be, you can divide and check yourself, 34602424. So, this gets to 34602424 divided by 0.5680406, 609,154.06 seconds. This is angle, this is angular velocity. So, this is the time on the right hand side, and this equal to 705.03943 days. So, here this delta theta b, remember while we go on this and look here in this place, delta theta b is this angle. So, this is the waiting time, this is waiting time on b. Delta theta b is nothing but a reflection of waiting time. Okay. So, this becomes your T W b, waiting time on b. So, he has to wait for, so waiting time on b will be T W b, this is 705.03943. And travel time is as usual, what was in the first part, the same thing is applicable here. So, conclude the result, travel time in ellipse, this is 832.82765 days. Waiting time on A, three 390.8253 days, and waiting time on B, so this problem is completed. Okay. So, this tells you what is involved in interplanetary transfer. So, if you have to send your satellite from Earth to Mars, so the same process exactly is involved, but the difference will be because the Earth is a big planet. So, its a gravitational field will affect the motion of the satellite which is sent from there. So, first it has to be sent in hyperbolic orbit, so that it comes out of the sphere of influence of the Earth, and thereafter it will go in elliptical orbit about the Sun up to the sphere of influence of, say, in this case the Mars, and thereafter in the Mars again it will enter into a hyperbolic trajectory, and at the perigee of the hyperbola then the satellite is to be captured inside the Mars. So, that we will look into for this problem. So, once we have finished this, so we have understood the principle behind this. Now, we can go for the this mathematical part of this. Okay. So, thank you very much.